Hi, everyone. Thank you for coming out. My guest today is David Sachs. He began developing motion sensing applications at the MIT Media Lab, and now he does advanced application development at InvenSense, where he does a lot of interesting things with compasses, accelerometers, and gyroscopes, including building them into Android devices. Please join me in welcoming David Sachs.
So the purpose of this talk is to learn about sensors that are in consumer electronics. These include accelerometers, gyroscopes, and compasses. It's kind of a zoo having all these different sensors out there. There's a big problem. People don't really know how to use them. They don't necessarily know what the sensors do or what their strengths and weaknesses are. They don't know how to put the data together. There's also a lot of misinformation out there about what's actually in different devices, and this causes a lot of confusion. So I'd like to pay my respects to some non-existent sensors, which you'll see in press releases. Even though they don't exist, people write all sorts of interesting stuff about them on forums. These include the 6-axis accelerometer, which apparently the Samsung Epic has, according to Sprint. The 6-axis gyroscope, the very mysterious gyroscopic accelerometer, and the gyro compass. The gyro compass, I have to say, actually does exist. There is such thing as a gyro compass. It's not shipping in any Android devices today. It looks kind of like that. Maybe someday. So this talk is going to start by covering some examples of applications. We'll show you some demos. Then we'll get into the more sciencey aspect of it. We'll talk about the sensors themselves, accelerometers, compasses, and gyroscopes. Then we'll talk about sensor fusion. How do you put this stuff together? System integration. And by that I mean, how did we make this? So this is a modified Nexus 1. It has accelerometers, compasses, and gyroscopes in it. It does sensor fusion, and we wrote a bunch of applications on top of it. In order to put the extra hardware in it, we had to rip something out first. So I'll leave you guys to try to guess what it is we ripped out. And you'll find out about halfway through the talk. And then, of course, really no one cares about all of this stuff. They just want to use sensor fusion. Most people just want to write applications that use motion. So hopefully this technology can make life easier for application developers. So they don't have to worry about what's an accelerometer, what's a gyroscope, what's a compass, how do you put all this data together. They just want to know how to use the information that comes out of it. So let's get started with some application examples. Gaming. Gaming's really fun. This party started with Nintendo. They did motion sensing gaming. Now everybody's doing it. So I'm just going to jump right in and show you some motion sensing gaming demos. So this is not a game. It's just a sword. But you can see it does what I do. That's pretty cool. So this uses gyroscopes, accelerometers, and compasses. Measures all sorts of orientation. You can see it's pretty stable. And it moves quickly when I move, and it stops when I stop. The latency is very low on this system, but I'm not sure if that will come through on the VC system. But that's not a game. I promised you a game. So here's a game. I'm flying through a tunnel. There's my tunnel. I can go left, right, up, down. I can turn sideways. I can fly upside down if I want. You have to fly through these doors. That's tricky to do while talking on the microphone. Yeah, that's a motion sensing game. Pretty fun. So we'll come back to this game at the end of the talk, and I'll tell you how we did this. Moving on. So here's some more applications. We have virtual reality and augmented reality. I've got virtual reality on the left, augmented reality on the right, and whatever the heck Street View is in the middle. I'm not sure. It's sort of like real virtual reality that's augmented or something. I don't know. But all of these use some motion sensing. So I'll show you this on our phone. It'll be kind of hard to see, but I'll have a video I can show you too. So here's our virtual reality system. I can look down. I can look up. I can look forward. Turn sideways. Pretty cool. So the motion sensing part of this is basically one line of code. Once you have your output of sensor fusion, you just draw some 3D stuff and put in your one line of code. So for those of you who can't see, here's a video of basically the same exact thing. This is an older system running on a G1, but it's really the same application. So you can see. So here it turns off the sensor fusion, so now it's just accelerometers and compasses, and it still works. Actually, you can do all of this stuff already, right? It's just a little bit slow. That's the main thing that all the sensor fusion adds. It just sort of upgrades the motion sensing capabilities. All right, so mouse. This is an example of a mouse that has gyroscopes and accelerometers in it, does some sensor fusion, and controls a cursor. Here's a demo of that. It's a gyro mouse. Pretty simple, right? It's very easy to do once you have all your sensor fusion done, basically. Again, it's just a couple lines of code to do something like this. So it stops when I stop, moves when I move, left, right, up, down. User interface. OK, well, user interface is kind of a zoo. There's all sorts of stuff you could do and call it user interface. I'm going to play a little video. We also have phones that run all of this stuff. You guys can play with it later on if you want. Here's what we did. We zoom in using motion. And you can pan around using motion also. You can do a lot of stuff that way using only one hand, which is kind of nice. Don't have to smudge your screen. And the pinch to zoom thing is kind of tricky to do with one hand. This is a little bit easier. Here's some more complicated stuff. So there's some gestures. You can draw a letter in the air, and that launches an application. You can also train a signature. So here he's training the letter M because his name is Mike. Once he's trained his signature, then he can go to an authorization application, and then instead of typing something in which would smudge the screen, he can draw his letter M in the air, and it unlocks it. If he draws some other pattern, it doesn't work. So these are examples of things that are pretty easy to do once all the sensor data has been put together, and you no longer have to worry about what's an accelerometer, what's a compass, what's a gyroscope. Image stabilization. We don't have a good demo of that here today, but it's something that people have been doing with these sensors for decades. And navigation, of course, this is a talk in its own. This stuff is pretty hard. We'll touch on it a little bit, but I won't get too deep into how navigation algorithms work. And of course, all of this stuff runs on a handset. That's why this is really interesting for Android. Once the sensors are abstracted out of the system and you just have the result of your sensor fusion data, then you can write apps that take advantage of all of this stuff. So let's jump right into the science part, talk about the sensors. Accelerometers, easiest to visualize as a mass on a spring. They're very simple. They sort of jiggle when you shake them. They pick up just about every kind of movement. That's the good news. The bad news is they pick up just about every kind of movement. Usually you have no idea what it is you're actually looking at. So here's some examples. The mass will droop under gravity, right? So that's pretty intuitive. In a real accelerometer, of course, you don't have these curly springs. You have beams usually that flex. If you drop it, it actually measures 0. That's kind of strange the first time you've played with accelerometers. That's free fall. And the reason why is because gravity pulls both on the mass in the middle and on the frame of the accelerometer. So there's no relative movement between the mass and the frame. So how is it that you measure gravity? Well, there's this additional force holding the structure up. So when you have that additional force holding the structure up, then the mass will droop under gravity. So this gives the kind of surprising result if you've played with accelerometers a little. If you point an accelerometer axis up, it will actually measure plus 1g. So you might have thought it would measure a minus number because gravity's pulling it down, but that's not the way it works. It's actually measuring the force of you holding the accelerometer up. So an accelerometer just exposed to gravity actually outputs 0. Of course, it also measures sideways movement. You shake it side to side, you accelerate it, the mass experiences a reaction force. And typically, you get something like this. So this is usually what you're looking at. It's just a big mess, and you don't know what it is exactly you're looking at. So that's an accelerometer. Here's one close up. Like I said, it's got beams that flex, not curly springs. This is using MEMS technology, pretty interesting. You can etch mechanical structures into silicon. So that makes it really cheap, and you can put logic next to it pretty easily. Compasses. So compasses no longer look like that. That's sort of what you imagine. Compass is a magnetic field sensor. It picks up every possible magnetic field. That includes the vibrating motor right next to it. If this is in a phone, it includes some stuff from the Bluetooth chip. It includes speakers, microphones, anything on the circuit board that's been magnetized. And it's kind of a train wreck, actually. I'm always surprised that these work at all in phones, but they actually work pretty well, considering the noisy environment. Why do you need a 3-axis compass? I get that question a lot. Well, if you have your compass held like this, and my x and y axes are flat, then I really only need the x and y axes to measure my heading. But if I hold my compass like this, now my x and z axes are flat, and I need an x and a z axis to measure my heading. So if you don't want to tell the user how to hold the compass, and you want them to be able to hold it any way they want, then you need a 3-axis compass, and you also need an accelerometer. So you can't compass at any orientation without an accelerometer to tell you how you're holding the device. Magnetic fields are kind of weird. The Earth's magnetic field doesn't point exactly north, so you need to know your GPS location to know where north is if you have magnetic north. And there's also something called magnetic inclination. The magnetic field's not actually horizontal. It's somewhere between horizontal and vertical. Here it's actually more vertical than horizontal. It's like 60 degrees from horizontal. But there's enough of a horizontal component to resolve your heading. Of course, when you get up to the north or south poles, then you're screwed. So how do compasses work? Well, this is how the compasses with the biggest market share work in consumer electronics. There's not a spinning needle. There's actually just current in a wire. And that current in a wire gets deflected by the Hall effect if there's a magnetic field present. So you can actually create a compass with just pure silicon electronics. You don't really need ferromagnetic material for it. And that's a close-up of a 3-axis compass. It has some Hall sensors and some logic. That's a compass. So now we get to gyroscopes. So gyroscopes are the newcomer. Gyroscopes sense angular velocity, so that's very different. They don't sense an external reference like magnetic north or gravity. Gyroscopes measure their own rotation. So how does that work? They use something called the Coriolis effect. So the Coriolis effect happens when you have a mass that's moving and your frame of reference is rotating. So when that happens, you get the fictitious force on the mass, and you can pick up how your frame of reference is rotating. So the Earth is rotating. So the Earth's rotation has some impact on things. For example, weather systems, the way weather systems spin in the northern or southern hemisphere depends on the Coriolis effect. If anyone ever told you that toilets spin one way in the northern hemisphere and the other way in the southern hemisphere because of the Coriolis effect, that's actually not true unless your toilet is like miles long or something like that, or perfectly polished. Anyway. Okay, so how do you actually pick up the Coriolis effect? Well, I said you have to move a mass, so you might as well move that mass back and forth really, really quickly. So that's what a gyroscope does. It actually oscillates. There's nothing spinning in a MEMS gyroscope. And it oscillates, and you can pick up the Coriolis effect from that mass oscillating by looking at something else that happens. So the mass oscillates, there's a torque that's provided, and then you can look at these capacitive sense combs picking up that signal. So this is slow motion, of course. Typically, these things oscillate at very high frequencies, maybe 25 to 30 kilohertz. So the actual frequency of oscillation, where you put that, depends on what else in the system you're trying to avoid. So if you're trying to avoid audio frequencies, or if there's another motor in the system that's going at some frequency, you might want to be careful about what frequencies you put your gyro at. And here's a close-up of a 3-axis gyroscope. So you can see these mechanical structures in that cutaway. These are the ones that vibrate and wiggle and sense and stuff. And then underneath is the silicon that has all the logic. So the bigger chip underneath does all the signal conditioning and actually does the sensor fusion. So this chip has a 3-axis gyro that actually does sensor fusion. It takes input from other sensors. So that brings us to sensor fusion. So how do you put all this data together? So let's start by putting accelerometer and gyro data together. Here's an example of accelerometers being used as a tilt sensor. So it basically works, but it's kind of noisy. So what does everyone do? They filter it. So here's a low-pass filter. It works, but it creates a delay. So that's why accelerometer tilt games are always kind of slow, because to get past all of this noise, you have to add a low-pass filter. So here's the gyro data. So the gyro data looks much nicer. It's really smooth, doesn't have that weird spike. But of course, gyro data isn't perfect either, right? Because gyro data, first of all, doesn't actually measure gravity, right? The whole point is to figure out your tilt with respect to gravity. Gyroscopes don't measure that. Accelerometers do. So we can put this data together. We get the nice dynamic response from the gyroscope, and we get the gravity measurement from the accelerometer. Then we have something that works well. So I'll give you a little demo of how that works. Okay, so here's just a little oscilloscope shot of a whole bunch of data. So if you look at the y accelerometer graph, that's on the middle on the right. You're right. Again, if I point the y-axis up, it measures 1g. As I point it down, it goes to minus 1g. So it's measuring tilt. That's that y accelerometer. It looks kind of noisy. That's my handshake actually being amplified a little bit because it's adding in the linear acceleration of my handshaking. And if I move quickly, you get these weird spikes. See that? Should get a square wave, but instead I get these strange spikes. Now let's look at the Z gyroscope data. So the Z gyroscope is this axis I'm rotating about now. And you get this nice big angular velocity signal on the Z gyroscope. But whenever I stop, it goes to 0. Gyroscopes don't actually measure gravity. They measure rotation. So wherever I stop, it's 0. So I need to put this data together somehow. So on the left, we have a signal we call gravity. So this is one of the outputs of sensor fusion that you might want in your application. If you compare y gravity to y accelerometer, you can see they look really similar, right? The y gravity is much smoother because that weird jittering thing is gone. If I move quickly, the spike is present in the accelerometer data, but not in the gravity signal. So that gravity signal is kind of strange. It's actually mostly gyroscope data, but with the accelerometer used to correct drift. So this gravity data is probably what you wish you had when you were writing your accelerometer-based game. What you really want is the output of sensor fusion, not just one sensor. So to summarize, what you do is you take the gyroscope, you get your orientation from it, and then you use the accelerometer to inject a correction term that keeps the orientation correct with respect to gravity and removes drift. So how did we get that orientation signal from the gyroscope anyway? So you have to do something called integration, right? So gyroscopes output angular velocity. What you really want is angle. So you do single integration. Integration's a little weird. The blue stuff is just noise that I generated, and the red stuff is the integral. And you can see that it has very different properties. So it looks less noisy, but more drifty. So intuitively, integration turns noise into drift. And that's actually one reason why the gyroscope signal is so clean. It's because it's integrated. And here's the math behind it. If you integrate a cosine, you get a sine, but you also get this 1 over f that comes out in front. That means if you have 100 hertz jittering on your gyro data from noise, when you integrate, that drops by a factor of 100. So you lose your noise. But on the other hand, if you have a very low frequency noise on the gyroscope, when you integrate, it gets amplified. So you have you get rid of your noise and you add drift. So integration is kind of a mixed blessing. So in order to do this well, you have to do it quickly. So here's a very simplified equation. You're integrating angular velocity, so you multiply it by time and accumulate it. That gives you your angle. Now, in order to do this well, the time has to be really accurate. So you're multiplying your gyro data by time. That means if your time is off by 5%, it's just as bad as if your gyro data is off by 5%. It's the same impact. And you also want your time interval to be really small. So what we do is we do it in hardware. So you can do it at a very fast rate. Basically, you have your sensors, then you have a separate motion processor, then you have an application processor. and the sensors in the motion processor, in our case, are on one chip, one piece of silicon. So that sort of abstracts out a lot of this high-rate integration stuff. So let's move on. So now we're going to combine compass and gyroscope data. It's basically the same story. Compass data gives you the answer you want, which is your heading, but it's noisy. It's noisy for two reasons. One reason is that it's picking up real noise, real signal. So we live in an environment that's magnetically very noisy. So, and these compasses, they pick up everything that's magnetic. The other reason is that it's not integrated, so it doesn't have that benefit of dropping the frequency component. So compasses, as we said, require tilt compensation. You can't figure out your heading unless you know where the horizontal plane is relative to how you're holding a device. Tilt compensation is done with accelerometers, but by themselves they don't measure gravity well. So you get this strange sort of bootstrapping that you have to do, where you have to tilt compensate the compass with accelerometers and gyroscopes before you can complete your sensor fusion. So in summary, it looks like this. Again, gyroscopes provide orientation. Accelerometers provide a correction due to gravity, and compasses provide a correction due to magnetic north. So I'll show you a little demo of that. So here's my sword again. This is using all the sensors together. So let's say I just use accelerometers and compasses. So it still works, gives me the right answer. It's just slow, right? There's this delay. Now let's say instead I use only gyroscopes. So gyroscopes have really good dynamic response. A perfect gyroscope, I could do this forever, and it would never drift. Of course, real gyroscopes drift, so this thing won't stay in the right place forever. But it looks pretty good in the short term. What you really want is all these sensors together. So now I have the gyroscopes providing the good dynamic response, and I have the accelerometers and compasses providing the correct answer in the long term. So that's my fused data. So now we get to position. So accelerometers measure side-to-side movement. So can't you get position out of them? Well, it turns out it's really, really hard. But let's talk about how that would work. So linear acceleration, which is what you want, just my side-side, up-down, and forward-backward movement, you have to take the accelerometer data and you have to remove gravity. This is called gravity compensation. So once I've removed gravity, whatever's left is my linear movement. Then you have to integrate it once to get velocity, integrate it again to get position. That's your double integral. Now if the first integral, a single integral, creates drift, double integrals are really, really nasty. They create horrible drift. Here's a graph of it. The red stuff is a single integral. You can see that random walk we talked about before. It sort of meanders off in some direction. And the green signal is the double integral. It's just taking off. Now this is integration of noise. So you can see this, this is simulating an accelerometer. I'm holding it in my hand, not doing anything. And it drifted off by 20 centimeters in 1 second. So I don't know, is that good or bad? Actually, I think that's pretty good. As you'll see in a second. But so 1 second of drift, 20 centimeters of error. That's from integrating noise. But that's not the problem. Here's the real problem. The problem is, remember back at the beginning of this slide when I removed gravity, well, I probably didn't do that exactly right. It's pretty hard to do that perfectly. So let's say I got it wrong. Let's say I thought I was holding this thing at 37 degrees, but I was really holding it at 38 degrees. So I screwed up my estimate of gravity by 1 degree. Well, now I double integrate that, I get a parabola. So I'm double integrating a constant, right? Here's what that looks like. So for comparison, the green line at the bottom is the same as the green line in the graph on the left. Now it just looks flat, right? So the new error is this blue curve. That's 8.5 meters of error in 1 second. So I was holding this for 1 second. I screwed up my orientation by 1 degree, and I got drift of 8.5 meters. So you can see why it's really, really hard to do any kind of linear movement. So step 1 is try to figure out how to avoid it in your application. Just use orientation. You'll be happy you did. There are some ways to improve the linear movement estimate. But if you're going to do linear movement, any kind of orientation error is really, really important. All sorts of errors couple in, including things like cross-axis error between the accelerometer and the gyroscope. Everything matters. So let's finish this off. I have my orientation estimate, and I add linear movement. So the way you do that is you first gravity compensate the accelerometer using the gyroscope. So in order to make sure I have the best possible estimate of which way down is, I need all of these sensors. Then once I have the best possible estimate of which way down is, I subtract that. Whatever's left is linear acceleration, and then I double integrate and pray. It still usually doesn't work that well. So here's some tricks. Well, what we have is at least better than a high-pass filter. That's what everybody's doing now. They want to make some game where you shake it. So they high-pass filter the accelerometer data. Whatever's left, they pray as your shake signal, and it really doesn't work. The reason why it doesn't work is because you're assuming that gravity changes slowly, but it doesn't. Gravity changes as quickly as I can do this. So gravity changes really fast because it's the gravity with respect to your device. So high-pass filters don't work that well. This works a little better. If you know something about how the device is moving, you can do even better by modeling your dynamics with something called a Kalman filter, which probably could be a completely different talk, so I'm not going to go into it in too much detail. But let's say these sensors are in a car. Well, the way cars move is very constrained. Cars can't accelerate in any possible direction. They're not going to go straight up, for example. So you can constrain your error using a model of how cars move. And a Kalman filter is a pretty good way to do that. That's for automotive navigation. If you're doing pedestrian navigation and you want to walk around, usually you use a pedometer algorithm. So you don't just double integrate the person, you watch for steps, and you do an algorithm based on steps. So those are 2 really common tricks to avoid your double integral. Okay, now before we move on to the next section, let's just cover a little bit of terminology. There's 2 different coordinate systems that are important. One is the coordinate system of the Earth, which includes gravity, includes magnetic north. If you're controlling a TV or a computer, it would include the TV or the computer. And the other is the coordinate system of the device that you're holding. So those are usually called world coordinates for the Earth and body coordinates for the device that you're holding. And then, accelerometers and compasses obviously measure relative to the Earth. They measure gravity and magnetic north. Gyroscopes are different. They actually measure in a different coordinate system. Gyroscopes measure in its own coordinate system. So it measures rotation around itself. And then just very quickly, the difference between degrees of freedom and axes. You see this thing a lot, 6-axis something or other. What does that really mean? Well, what people really want is 6 degrees of freedom. That means I can move left and right, that's 1. Forward and backward, that's 2. Up and down, that's 3. And then you also have rotation around the 3 axes. That's we're going to call that roll, pitch, and yaw, although we'll define that a little better in a second. Those are 6 degrees of freedom. 6 axes usually just refer to the axes of the sensors. So 6 axis can mean almost anything, which is why it gets abused a lot in marketing. I have a 6-axis sensing device. I have no idea what that means. You could have a 1-axis accelerometer. You could have 6 of them in a row and call that a 6-axis sensor. Some people, when they say 6-axis, they mean accelerometers and gyros. Some people mean accelerometers and compasses. Anyway, so 6 degrees of freedom versus 6 axes, at least know what they mean. Okay, so now we get to system integration. So that's the part where we built this. So what we ripped out was the headphone jack. That was probably the most fun part. Then we took a little board and soldered it to the I2C bus, and then we started hacking Android. So here's what we did. Actually, the first thing we did is we just built our own JNI wrapper around our own library using a standard Linux I2C driver. So that's not really using the sensors within Android. That's sort of using the sensors near Android or something like that. This is what we did in our second draft. it's a little bit tricky because right now there isn't really a great way to do a whole bunch of math on these sensors in post-processing. So for example, we could put it in the kernel, but we don't really want to put our stuff in the kernel. We could put it in the user space, but then it gets copied. So if you put too much stuff in the sensor manager, you get all these copies of the sensor manager. So what we ended up doing was actually hacking the sensor service, which is not really what you're supposed to do, but it actually worked pretty well. So we put our driver in the sensor service. It talks to our sensors through a standard I2C driver, and then it sends data out to the sensor manager. We're not really thrilled with it, but it actually works pretty well. We're working on a new version of this that will be a little more efficient, but this is sort of where we are right now. So maybe that doesn't matter to you. You just want to know how to use this data. So here's what comes out. So you've got your sensor manager, right? You want to write an application that uses sensor fusion. Here's what you have right now. You have some raw data, and you also have some compass and accelerometer functions. So we added a whole bunch of other sensor fusion stuff. So we have, for example, a quaternion output, which we use to do a lot of stuff. We also have rotation matrices and Euler angles. And then we also added a bunch of higher level algorithms on top of that. So our gesture, pedometer stuff, the signature recognition we call glyph. That's where we train characters. So this is our entire library that we exposed through the sensor manager. We're not really sure where these higher level functions should go, but we stuck them in the sensor manager and it worked for us. And then of course all that stuff just goes up to the application. Okay, so here we get to the final section. So here's how you use sensor fusion. Well, first of all, what comes out of sensor fusion? Well, we have this gravity vector we mentioned and a linear acceleration. So one way to think about this is you have your accelerometer data. It's really the sum of two things that you wanted separately. So sometimes you want gravity, sometimes you want your linear acceleration, but what you ended up with was the sum. So sensor fusion basically helps you separate them. So then you have gravity separate from linear acceleration. If you added them back together, you'd get this raw accelerometer data. Then we have orientation. Well, orientation's kind of a crazy zoo in itself. So there's all these different ways of expressing orientation. Euler angles, rotation matrices, axis and angle, quaternions. Maybe you just want the change in your rotation. So we're going to cover all of these just a little bit and talk about how you would use them in an application and have a couple lines of code for each. And of course, the other thing that comes out of sensor fusion is better raw data. So all of these sensors, they have problems, but luckily they have different problems. So since they all have different problems, they can calibrate each other. One sensor can make another sensor better. Okay, so very quickly, gravity. Well, you know what that is. It's that thing everyone's using to write their tilty games with, right? Except it doesn't work that well. It should be easy to port your existing accelerometer code. Basically, you rip out the accelerometer stuff and you put in gravity. It should just work better. And you can take out that low-pass filter that you've been using because you don't need it anymore. So that's gravity. That's probably the easiest one to know how to use if you already know how to write a tilt game with accelerometer data. You can just immediately do a better one that uses all of the sensors. Linear acceleration. So that's for shaking games or something, side to side, up and down. Again, you've already tried to do it with accelerometer data. It didn't work that well. It should work a little better just by putting in linear acceleration data. All you need to do now is take out the high-pass filter that you've been using, which didn't really work anyway. I'm going to demo that one quickly because that's not completely intuitive. Okay, so on the left, we have linear acceleration. On the right, we have raw accelerometer data. So you notice, again, the y accelerometer data measures gravity as I tilt back and forth, but the y linear acceleration data does not. So it stays at 0 because I'm not moving sideways. If I go up and down, both of them measure that, right? So the y accelerometer and the y linear acceleration both measure this up and down movement, but the y accelerometer has this bias error. That's because it's measuring the up and down movement plus gravity. So it's measuring both of them. Whereas y linear acceleration has had the gravity removed by the sensor fusion process. Yeah. So if I turn it upside down, I get the bias in the opposite direction. Right. Okay, so now we get to the last part of the talk, which is how do you express rotation? Expressing rotation is actually really, really hard. So we have to spend at least a couple minutes on it. Really the problem we're trying to solve is how do I say what happened to the green teapot to make it the blue teapot? Something happened to it. It rotated. But how do you write that down? Turns out there's a few ways to do this, and all of them have some problems. It's good to understand how they work if you want to use this stuff in an application. So let's compare it to linear movement. So for example, let's say I have some arbitrary linear movement I want to express. That's that diagonal green line. Well, I can express that as the sum of a vertical movement and a horizontal movement. So that's great. That works really well using vectors. I can go the other way too. I can do the horizontal movement, then the vertical movement. Works great. So what if I try this with rotation? Well, it turns out it doesn't work that well. So let's say I take my teapot, rotate it around the handle, then rotate it around the spout. Well, here's where I ended up. Let's try it again. Take my teapot, rotate it around the spout, then around the handle. Well, I ended up somewhere completely different. So rotation inherently is messy. It doesn't work as well as linear movement. So what are we going to do? Are we screwed? There's a couple ways of expressing rotation that work pretty well. So we'll talk about those. This one's really cheating, but I like it. Let's forget about rotation and just talk about the change in rotation. So from one point to the next, how much did I rotate around the y-axis? How much did I rotate around the x-axis? If you do this for a while, you're not going to get anything that accurate, but it turns out it works really well in the user interface. For example, let's go back to the gyro mouse. So again, I moved left, right, up, down. Works pretty well, right? Well, this is easy, actually. All I'm doing is looking at the change in rotation around one axis and mapping that to a movement of pixels, left and right. I can look at the change in rotation around this axis and map it to pixels moving up and down. So it makes it seem linear. That's why it's nice for a user interface. So to summarize, you look for your change in angle, which really should be between two rotation matrices. It's not that accurate. It's easy to map to stuff. And you can do it in a couple lines of code once you have it. So if your sensor fusion outputs what you want, which is angle change, then here's all the code you need. So for example, we use this in panning when we pan in an image. It's really simple. Just accumulate your angle change in your pan variables and then use a GL translate. 3 lines of code to make a motion-based panning system. Okay, so now we get to Euler angles, named after this guy. Yes, it's pronounced Euler. I'm not sure why. But everybody loves Euler angles, even though they actually don't work that well. We'll explain why they don't work that well. So again, we want to get from the green teapot to the blue teapot. So we can express that as a series of rotations. So we're going to rotate around the vertical. We'll call that yaw. We're going to rotate that around an axis through the side of the teapot. We're going to call that pitch or elevation. And then we'll rotate through the spout, and we'll call that roll. So if you look at my arm, this is yaw. That's also called heading, just which direction you're looking. This is pitch, also called elevation. And then this is roll, rotation around the axis through my forearm. Now we have a problem. What if I point straight up and do this? Is that yaw or is that roll? Well, I'm sort of changing my heading, and I'm also rotating around an axis through my forearm. And actually, it turns out when you point straight up with Euler angles, everything breaks. And I'm going to demo everything breaking. It's really important to understand that this happens. Euler angles work okay for these guys. So in a lot of navigation systems, they use Euler angles. So is it a problem that you can't point straight up or straight down? Well, it depends on your application. Let's say your application is a passenger jet or a car or a submarine. The fact that you can't point straight up or straight down is not really a problem. If your pitch goes to 90 degrees or minus 90 degrees, really it'll be the least of your worries that the Euler angles aren't working. So let's use it in an application. Just be careful. Don't let your pitch go to 90 degrees. there's tricks you can use to get around that. You can sort of change your definitions on the fly. So if this is my forward direction, as I start to point up, I might run into trouble because my pitch is going to 90 degrees. Quick, let's redefine this as forward. So now my pitch is 0. People play all these games. They're really messy. Personally, I try to avoid using Euler angles unless I have to. Here's some code. So once you've got some Euler angles, you can do a pitch and a yaw rotation, for example. Here's another example. Sometimes you get lucky and someone provides an API that takes pitch and yaw. So let's look at a demo of that. So of course, I always go to the Grand Canyon with Google Earth. OK, so I got my yaw, and let's call that pitch. I can turn sideways. This is pretty fun. So with a very small amount of movement, I can control which way I'm looking. I go like this. I can look down. OK, so where do I run into trouble? Well, let's say I point straight up. Hey, it works fine. So that's because I cheated. This is actually roll. So I switched pitch and roll to make it work. That's another messy game people play. So I'll show you pitch. Now, as I turn sideways like this, eventually my pitch goes to minus 90 degrees, and my Euler angles should explode. There they go. OK, so it's important to know that this happens, right? If you're going to use Euler angles. But it does work, right? It worked great till I did the thing I wasn't supposed to do. So if you constrain your application, Euler angles actually work just fine. OK, so now we get to rotation matrix. Again, we want to go from the green teapot to the blue teapot. Here's a rotation matrix. Basically, multiply it by any point on the green teapot. It gives you the point on the blue teapot. So from that definition, it's pretty simple. It's 9 numbers. What do those 9 numbers mean? Should I just ignore them and just use it as a matrix and multiply things by it? Actually, I like those 9 numbers. I like to use them for things. Here's a good way to visualize them. If you picture x, y, and z axes sticking out of the teapot, those axes twist around with the teapot. You got 3 axes. Together, that's 9 numbers. By coincidence, those are the same 9 numbers in your rotation matrix. So for example, if you have a rotation matrix and you want to know what's the direction that stuff will come out of the spout of the teapot, you actually already have that information. It's just a vector that you can pull directly out of the rotation matrix. So sometimes you can just take numbers out of the rotation matrix and map them to things. Here's how you use a rotation matrix. You can use it to rotate stuff in OpenGL. So there you go. There's one line of code to use your sensor fusion in an application. You just multiply by your rotation matrix, and you're basically done. You got to be careful because OpenGL actually defines their matrix like that. So you might have to add some zeros and a 1. And of course, you can also just, like I said, pull numbers directly out of the rotation matrix and use them for things. Just look at the numbers, and sometimes they're useful. OK, so a couple more. Axis and angle. Well, you can express the rotation of the teapot from green to blue as one rotation around this axis by this angle. So that's sort of interesting. Any rotation, no matter how weird it seems, you can write it down as one rotation by one angle around one axis. So you need 4 numbers here, the angle, and 3 numbers for your axis. We'll come back to that in a second. But first, quaternions. So these are my favorite. Everyone hates them. People are scared of them. They actually work really well. I think people are scared of them because if you look them up, you get stuff like 4-dimensional vector that lies on a hypersphere. That's a hypersphere. Actually, you can't really draw a hypersphere, so that I think the picture said 2-dimensional projection of 3-dimensional projection of hypersphere, or something like that. Anyway, I don't really care because quaternions basically axis and angle. You can use it like that. If you don't believe me, that's a quaternion. Look at the numbers. There's x, y, and z. It's your axis, and there's theta. That's your angle. So most of the time, that's how you use it. So here's how you use a quaternion in one line of code, glRotatef. There it is. This is how that sword worked. This is also how our little virtual reality demo works. There's really one line of code to do all of the motion sensing in that application, and that's the line of code. So you pull out the angle from the first component of your quaternion, and then the other 3 become your axis. It's pretty simple, actually. Quaternions, the reason why people like them is because you can do stuff like interpolate between them. Don't try interpolating between two rotation matrices because it usually hurts. Euler angles also hurt. You can do it with quaternions. So let's say I don't like my green and blue teapot. I want to find the one right in the middle, or I want to extrapolate and find the next one. That's pretty hard to do with anything except quaternions well. And that's basically it. I'm going to show you one more demo. So here's my my flying game again. Where's my tunnel? So let's just summarize everything that we did. So this flying game uses vectors from the rotation matrix to figure out which way I'm pointing. It uses roll from the Euler angles. So you can use Euler angles in this game, right? Because I can't point straight up anyway. I'll bang into the tunnel. So sometimes you can constrain your application so Euler angles work. We also use linear acceleration in this game. If I punch forward, it speeds up. If I pull back, it slows down. And so there you go. There's your sensor fusion. Okay, that's all. Thank you.